Hello, I am Abhishek Desai from Team 10, and our topic for the NNDL project is Predictive Analytics in Credit Risk. So, our motivation for this project stems from the increasing number of loan applications due to the technological advances and the subsequent challenges that the bank face in efficiently assessing the loan worthiness. The objective of our project is to harness machine learning methods to boost accuracy of predictions in loan approvals. We will further discuss how we applied various supervised learning models to predict loan approval outcomes based on the different applicant features. So the dataset that we chose for baseline model was an open source dataset readily available on Kaggle. So the dataset was of CSV format and it consisted of different inputs such as the loan ID, the gender of the applicant, then the marital status, the number of dependents an applicant has, what is the education of the applicant, what is the loan amount that the applicant is looking for, loan terms, etc. And the final output was whether the loan status is approved or rejected. So this is the CSV file of the baseline data source. There were a lot of different challenges that we faced with respect to this data set. First of all, there was an imbalance in the classes in the data set. We observed that there were a lot more loan approved status compared to the loan rejected status. Then there were a lot of missing values and null values in the data set. And thirdly, there was a limited quantity of data. The data comprised of less than 500 rows. So we implemented different solutions for this. First of all, we handled the missing data and outliers. We used the mode method of fill-in. So the baseline model we selected was random forest. We selected this due to its accuracy, simplicity, and speed of execution. So a random forest builds multiple decision trees during training and it outputs the class that is the mode of the classes. So a random forest is versatile and it naturally handles the missing values and maintains accuracy for large databases. So here, as you can see in the model configuration, we have set a parameter grid. So we are using grid search CV to find the best parameters, and as you can see here, we got the best parameters, for example, with a classifier max depth 6, classifier max features 0.7, etc. So as you can see, our random forest algorithm got a training accuracy of 87% and a test accuracy of 81%. We tried using different hyperparameter tuning, but still the test accuracy wasn't increasing beyond 81%. And this is due to the fact that there was very limited amount of data. The current data consisted of just 350 records. So hence we decided to go ahead with a better data set. So this is the data set that we decided to go ahead with. So this data set is an open source data set readily available on Kaggle. So this consists of more inputs compared to the previous data set, and this consists of a lot more number of records. So this data set consists of like 250,000 records, and it consists of inputs such as loan ID, the income, the credit score, the interest rate, etc. And the final output consists of whether the person taking the loan is going to default on the loan or not. So this is the CSV file. So for the final model selection, we considered different models such as random forest, gradient boosting, naive Bayes, decision tree, KNN, MLP, and an ensemble model. So what we observed was that we got the highest accuracy using the ensemble model, which consisted of a light gradient boosting machine and a multi-layer perceptron, and the accuracy was 88.78%. So this is the architecture of the multi-layer perceptron that we have used. So the input layer, it matches the number of features that are present in the data set. The first hidden layer consists of 128 neurons. The second hidden layer consists of 64 neurons, and the third hidden layer consists of 32 neurons. So each hidden layer also includes a ReLU activation function for nonlinear transformations. So We have also incorporated the dropout layer after the first and second hidden layers, and we have set the dropout rate to zero point 0.3 to reduce overfitting. And the output layer, it consists of a single neuron with a sigmoid function to output the probability of a lone default. So the second model that we've used in the ensemble model is light gradient boosting machine. So this is the configuration that we had set. So the metric that we're using is binary log loss. So it basically quantifies the accuracy of the classifier by penalizing the false classifications. The boosting type that we're using is GBDT. So GBDT builds trees one at a time, where each new tree helps to correct errors made by the previously trained trees. Then the learning rate, we have set it to 0.05, which basically controls the speed at which the model learns. We've set the number of leaves to 31. So this basically defines the maximum number of leaves in one tree. We haven't set the max depth, so this would allow the tree to grow as deep as necessary. Then we have set the minimum data in leaf to 20, which ensures that a sufficient number of samples in each leaf to prevent the overfitting. And we've set the max bin to 255, which is the maximum number of bins used for binning continuous features. An ensemble method combines multiple algorithms to achieve better predictions. So this also reduces the likelihood of overfitting, and it makes the algorithm overall more robust. These were our ensemble method results. The future direction for this project would be to improve the accuracy by performing more hyper parameter tuning with respect to the ensemble models. Thank you.